Hi. In this video, we're going to begin our discussion of determinants. At the end of this unit, you should be able to define what a determinant is, be able to manipulate algebraic expressions of determinants, to be able to compute determinants in various ways, determinants of 2 by 2 and 3 by 3 matrices using direct methods, determinants of general n by n matrices, either by recursion or by LU decomposition, and to be able to use the determinant to assess the invertibility of a matrix. Let's begin with defining the determinant and some of its properties. What is a determinant? Perhaps the simplest definition, or the most intuitive definition of what a determinant is that it is an algebraic expression in terms of the elements of a matrix that can be used to determine whether the matrix has an inverse or not. And it has the property such that if a matrix has a determinant of 0, it is singular, the inverse does not exist, while if the determinant is 0, the matrix is non-zero, the matrix is non-singular. So a number that we can associate with a matrix computed from the elements of the matrix that can tell us whether or not a matrix is singular or not. Just as the matrix inverse is only defined for square matrices, and we reserve the terms singular and non-singular for square matrices, the determinant is only defined for square matrices. Let's take a look at a couple of simple examples to illustrate what we really mean by this, and to see where this takes us in terms of a method to compute it. Let's start with a 2 by 2 case. Remember, we want a determinant to be an algebraic expression that tells us whether or not the matrix has an inverse. If we take a generic 2 by 2 matrix, we can carry out elimination on this matrix. As long as A is not 0, we use A as a pivot to eliminate downwards. This zeroes out the entry below that, and we do this by subtracting C over A times the first row from the second. This gives us, in this second position of the second row, D minus B times C over A, which we can simplify or use a common denominator form to write as AD minus BC over A. In order to do this, A had to be non-zero. The inverse will only exist if this second pivot here is not 0. If this is not 0, then the matrix is non-singular. Sufficient to tell us that this is non-zero is asking if the numerator is non-zero, and so we can define a determinant as AD minus BC. If this number is 0, the matrix will be singular. If it is non-zero, it won't be. We had a special case here of A equals 0. It can be shown that this still holds true for the case where we relax that, but I don't want to go through that here. So for the 2 by 2 case, we can define a determinant, a simple algebraic expressions of the elements of the matrix. If the determinant is 0, the matrix is singular. If the determinant is non-zero, it is not. Let's move on to the 3 by 3 case. If we try to do the same thing, we can do so, but it immediately gets messy. I am demonstrating this here, not to work through all of the algebra, but simply to demonstrate that it is possible to do this. We can start with a pivot. As long as this entry is non-zero, we can use to eliminate downwards. When we do so, we get these terms that look just like that d minus bc over a term from the previous example, but dependent on what all of the elements were. We can then use a second pivot to eliminate downwards. And this gives us a very sort of nasty expression that we can try to simplify. And it turns out that we in fact can simplify this down. We can multiply out the numerator, find out that there are a couple of terms that cancel out one another, and then there's another common element in the numerator and the denominator that cancel out. And this leaves us with, again, a ratio that can't be equal to 0. The inverse exists if and only if the numerator is 0. And this can be used to define an expression for the 3×3 determinant. This does not seem to be a productive way to move forward for evaluating determinants, to understanding determinants. The 2×2 case, we came to a nice clean result. The 3×3 case gives us something very messy and required a lot of algebra to get there. Instead of trying to push forward with this brute force approach to try to understand the general determinant, let's take a step back, recognizing that it seems that the 2×2 and the 3×3 case can give us an answer, but perhaps there is a more intuitive way to go about understanding these ideas. Let's begin with a discussion of a more general form, but a simpler case. The triangular case, a case where we have a triangular matrix. I've shown this in the case of an upper triangular matrix, but we could also have get the same result from a lower triangular matrix. Now, for a triangular matrix, we are already in what seems to be an echelon form, an upper triangular form. The inverse will exist only if we have a full set of pivots. What does it mean to have a full set of pivots? It means all of the diagonal entries have to be non-zero. A sufficient condition for saying that the matrix is non-singular, and a necessary condition, is that every one of the diagonal elements is non-zero. How can we express that idea as a single algebraic expression? We can multiply them all together. And if none of the entries are 0, their product can't be 0. If any of the entries are 0, their product will be 0. So we can define a determinant for this matrix as the product of the diagonal entries. This is scalable. This allows us to find a determinant for any size matrix, but is restricted to the triangular case, upper or lower, as it may be. Okay, with that, let's introduce some of the properties that the determinant has. We're not going to derive these for the time being. In a subsequent video, we will explore some more definitive proofs or definitions, some more rigorous definitions for what the determinant is, and this will allow us to prove these properties if we wished to do so. But for now, let's take these as givens. First of all, the determinant of the identity matrix is 1. This follows from the result that we just discussed. The identity matrix, of course, is a diagonal matrix with zeros everywhere else. That is a special case of a triangular matrix. The determinant must be the product of the diagonal entries, and the diagonal entries are all 1, so the determinant is 1. We've already discussed how the grounding idea of the determinant is that it should represent, allow us to indicate whether a matrix is singular or not. The determinant of any singular matrix must be 0. What this means is that any time as soon as we can identify a matrix being singular, we know that its determinant must be 0. If a matrix has identical rows, if a matrix has identical columns, if a matrix has a 0 row or a 0 column, or rows that are linear combinations of other rows, that tells us that the determinant must be 0. We've done a lot with manipulating matrices to transform them into forms where we might recognize if there are 0 rows or 0 columns. For example, to say that a system doesn't have a solution, or to manipulate it into an upper triangular form in order to use back substitution to solve a system, to manipulate a matrix into the identity matrix in order to find an inverse. How might these row manipulations that we apply to Gaussian elimination impact the determinant? If we could understand that, perhaps we could use those tools to help compute determinants. So let's review some of those properties. Remember that there are 3 fundamental row operations we can apply. We can exchange 2 rows of a matrix. We can scale a row of a matrix, multiply a row by a scalar, or we can add or subtract a scalar multiple of one row to another. And these are really any other row manipulations or combinations of these. And elimination, the whole process of forward elimination, back substitution, involves only these 3 types of operations. Each of these has a very simple effect on the determinant. Exchanging 2 rows changes the sign of the determinant. I should be clear here. I might not have emphasized this clearly enough. There are 2 notations that we use to denote the determinant. We sometimes use the letters DET and write det A, meaning determinant of A. We just as often use single vertical lines on either side of the matrix, similar to the way that we denote the absolute value of a scalar. When we are working with a matrix, the lines, single bars, mean the determinant in all cases. This is a universal notation, as is the first. When we exchange rows, we change the sign of the determinant. When we scale a row, that is, we multiply a row by a scalar, we scale the determinant by exactly the same amount. So multiplying one row by k multiplies the determinant by k. And adding a scalar multiple of one row to another doesn't change the determinant at all. This might be surprising. This might seem to be a larger manipulation of the matrix than row exchange or scalar multiplication. And while both of these have relatively modest changes to the determinant, they do change it. This perhaps more substantial modification to a matrix, adding a scalar multiple of one row to another, doesn't change it at all. This is going to be very important because remember, the core steps of forward elimination involve repeated applications of this particular step, which won't change the determinant. This is how the operations of row operations affect determinants. How do some of the simple algebraic manipulations or other manipulations of matrices affect the determinant? We're going to consider 3 examples. The product of a matrix. If we have a matrix that is defined as the product of 2 other matrices, of course, these both have to be square matrices, which means C also has to be a square matrix of the same size. The product of 2 square matrices is equal, the determinant of that product is the product of the determinants. Very simple relationship. The determinant of the inverse of a matrix is the inverse of the determinant. The determinant of A inverse is simply 1 over the determinant of A. Of course, the inverse only exists if the determinant is non-zero. 0 is the case where this would fail. This makes sense. It's all consistent. A 0 determinant means we cannot compute a determinant for the inverse because the inverse does not exist. Finally, a matrix has the same determinant as its transpose. Before moving on, I want to highlight, mention one other sort of rule that you might wonder about. What is the determinant if we multiply a matrix by A? What is the determinant of C? It is not K times the determinant of A. Rather, it is K to the power of N times the determinant of A. Why is this? This is because scaling a whole matrix by K involves multiplying every single row by K, and each row scaling increases the determinant of A by a factor of K. So we have to do that as many times as we have rows. This form, scalar multiples of A and trying to propagate determinants through it, this doesn't arise nearly as often as propagating determinants through matrix products. And so it's something to keep in mind, but it's not really a central core idea that you need to remember. Okay. With this, we're all set to make a deeper connection between Gaussian elimination and how we can compute a determinant. Let's think about Gaussian elimination, especially the forward steps, as represented by LU decomposition. We take a matrix, we apply some row exchanges to a matrix A prime, then we apply elimination steps to an upper triangular form. And we represent this as PA equals LU. As long as A is square, U will be square. P and L are always square, have the same number of rows as A. So if we start with a square matrix A, all of these will be square matrices of their same size. They're all square matrices of the same size. We can take the determinant of this product, and we get the relationship that the determinant of P times the determinant of A equals the determinant of L times the determinant of U. And we can rearrange this. Remember, the determinants are just numbers to give us the determinant of A as the product of the determinants of L and U divided by the determinant of P. At this point, it doesn't look like we've made anything easier. We've replaced one determinant with three determinants. However, each of these are easy to evaluate. First of all, we can think about P. P is a permutation matrix. It only represents rearranged rows. The difference of it from an identity matrix is simply from row rearrangement. The only thing that row exchange can do is change the sign of the determinant, and the identity matrix has a determinant of 1, which tells us that the determinant of a permutation matrix must be plus or minus 1. L, sorry, I'm missing an L in here. L is a lower triangular matrix with 1s on the diagonal. Remember that the determinant of a triangular matrix is just the product of the diagonal entries. If all of the diagonal entries are 1, then the determinant of L must be 1. If the determinant of L has to be 1 and the determinant of P has to be plus or minus 1, this expression simplifies down to the determinant of A is plus or minus the determinant of U. We can carry out elimination and compute the determinant of U. U is an upper triangular matrix whose determinant is also determined simply by the product of its diagonals. This gives us a general way to compute the determinant of any matrix using elimination. We really take 3 simple steps. We first of all perform forward elimination to an echelon form, being careful not to do row scaling. Remember, not to multiply rows by scalars in order to simplify the arithmetic in some way. If we do that, it changes the result in a way we would have to keep track of. This is the same requirement as we need in LU decomposition. So perform forward elimination to an echelon form. The product of the diagonal entries of U, because this is a upper triangular form, gives the determinant of U and gives the determinant of the original matrix up to a sign. So plus or minus whatever the determinant of U will be A. How do we determine what that sign is? We simply have to count the number of row exchanges. Right? Remember that the identity matrix has a determinant of 1. So if 1 row exchange was involved, it would change the determinant, would make the determinant of that permutation matrix -1. If there were 2 row exchanges involved, it would make the determinant 1 again. If there were 3 row exchanges, it would make the determinant -1 again. We count the row exchanges. If there were an even number, then the determinant of A is just the determinant of U. If there were an odd number, then the determinant of A is negative the determinant of U. Perhaps the best way to illustrate this is with an example. what is the determinant of this matrix? Here's a good time to note another form of notation. We very often indicate the determinant of a matrix of numbers by replacing the square brackets around a matrix. So let's say I write something like this. This indicates a matrix of values A, B, C, D. The determinant of this matrix is very often written just replacing the square brackets with vertical lines, the symbol for the determinant. This is something that is important to get used to so that you can distinguish a form as shown in the problem here. The determinant of this matrix equals what, and that we can distinguish this from the matrix itself as represented in elimination. Okay. So we have a 4x4 determinant, a 4x4 matrix. We would like to evaluate its determinant. How do we do this? Using elimination. We start with our matrix, call this A, and perform elimination as we should be very familiar with now. Eliminate with our first pivot downward. Subtract 2 times the first row from the second. Gives us 2 minus 2 is 0, 2 minus 4 is negative 2, 2 minus 2 is 0, and 1 minus 4 is negative 3. Subtract the first row from the third, gives us 1 minus 0, 0 minus 2, 1 minus 0, and negative 2 minus 2 for the third row. And we add the third row to the second row to get, to the fourth row to give us 0, 4, 3, and 6. Move down and over to our next pivot and eliminate downwards again. Subtract the second row from the third. Negative 2 plus 2 is 0. 0 plus 0 is 0. And negative 4 plus 3 is negative 1. Add 2 times the second row from the fourth. 4 minus 4 is 0. 3 minus 0 is 3. And 6 minus 6 is 0. Move down, and we have a 0 where we would like a pivot, but a non-zero entry below it. We exchange rows. Let's count that row exchange. After doing so, we are now in our upper echelon form. We have 4 non-zero pivots. This matrix is non-singular. It has an inverse. We're not interested in computing the inverse. We're just interested in computing the determinant. We compute the determinant of u by multiplying these entries. 1 times negative 2 times 3 times negative 1 is positive 6. And then to get the determinant of A, we have to address the question of row exchanges. We applied one row exchange, so we have to change the sign to a negative 6. The determinant of A is negative 6. All right. That wraps up our introduction to the properties of the determinant. There will be an accompanying video where we do some more examples using the properties of the determinant, and a subsequent conceptual lecture discussing the more formal definitions of what the determinant is and how we can use that. Thank you, and goodbye.